let's start. So it is a pleasure to present my dear friend Paulo Natenzon from WashU, who's going to talk about random choice and differentiation.
Thank you so much, Leandro. It's a great pleasure to be back here. So many memories from the time I was a student, and so many mentors and peers in the audience. So thank you so much to the organizers for having me, and it's really a pleasure to be in this very distinguished lineup of fancy presentations. So I'm going to give you a talk about random choice and the role of differentiation for choice. And some of you have seen preliminary versions of this paper, and it has evolved quite a bit. And so I'm looking forward to continuing the conversation and getting more feedback until this thing is finally published. So this is joint work with my student, Junan. He's at Sciences Po. He's an amazing kid, and you'll see him do amazing things in the future. So here's the motivation. I'm going to tell you what I'm going to study and why it's important to study it. Okay. So the variable that I'm interested in is product differentiation. Okay. And so why is product differentiation important? So if you have had a class with the logit model, you know the logit model lacks something very important. The logit model doesn't allow for product differentiation, doesn't allow for any horizontal differentiation, and that leads us to a series of problems. The main issue is, for example, in I/O, you want to capture the fact that some objects are more similar than others. Okay, so if you have two minivans, and you want to have a demand system, and you want to predict what will happen when you raise the price of one of the minivans, let's say that we make this minivan more expensive. You know that some of the population, that this minivan is going to lose market share. Okay, so now it's natural that the person that gives up on buying the first minivan because the minivan got a little too expensive for them is more likely to switch to another minivan than to switch to a coupe. Okay, and so the logit model can't do that. If they start with the same market shares, then the model will say that the person who gives up on buying this minivan because of a price increase is equally likely to go to each one of these. So we need to account for the level of differentiation between the products if you want to properly specify the demand system and make predictions. Very related to that, in behavioral economics, when people are making mistakes, in psychology and even in biology, the level of differentiation of the options also affects something very important for us to fit and predict behavior of a sample, which is the level of the easiness of comparison. So this is another experiment in psychology by Tversky, where prisoners were trying to guess which one of these rectangles has the largest area. Okay? So you saw a bunch of pairs of rectangles. You're trying to guess which one is the bigger one, which one has the largest area. And if you get it right, then Tversky will pay you with cigarettes, because in the 70s, the IRBs will allow you to pay the experimental subjects with cigarettes. So 85% of the subjects correctly identified this rectangle as being bigger than that one. Okay? And these two rectangles have exactly the same area, so it was a 50-50. But you notice that the first rectangle and the third rectangle, only 67% of the subjects correctly identified the one on the left as being the bigger one. Okay? So if, like in the logit model, you only have one variable, which is the size of the rectangles to explain this, you can't do it. Because these two have exactly the same size, so they have the same utility. That means that the gap in value between each one of these on the right and the one on the left is the same. So you need something else to explain why is it that these two are easier to compare than these two. And again, you can think of this as some form of similarity or differentiation between the objects. You need a second dimension to say these two objects are more similar to each other and therefore easier to compare than these two. Okay. And it will turn out that the framework that I'm going to show you today, and the representation theorem I'm going to show you today, is going to allow me to have a variable that captures the level of differentiation of the options, which you can use to study and bring to data in things in psychology like this, when you're trying to explain the mistakes that the agents make in choices, and also to bring it to demand systems and do I/O, taking into account the level of differentiation of the options. Okay, so this is what I'm doing, and this is why it's important. And I'm going to give you now I'm going to give you one slide to tell you what the data is like, or what is my primitive, and then I'm going to give you the main theorem straight away. So we're talking about probabilities of choice when individuals are making repeated choices, or when you have a population coming to the lab trying to guess the rectangles. Or you could be talking about the market shares. Okay, so what you have as a primitive is a random choice function. I'm going to call it rho of object x when the options are x, y, and z. okay? And that is the probability that X is chosen from the menu of options X, Y, and Z. Or you can also interpret it as the market share of product X when these are the available products, okay? And of course, they have to add up to 1. In the special case of binary choices, when I'm doing binary comparisons in the lab, or when I only have a duopoly, I'm going to use the notation rho of X, comma Y to be the probability that X is chosen when X and Y are available, okay? So this object here is my primitive, is what we're going to call the data that I get to work with. Good. So what do we do with this data? I'm interested in what are the conditions under which I can interpret data as being generated by this formula. Okay. So the representation theory we're going to have these objects are going to live in Rn, or in any finite dimensional vector space. And the probability that X is ranked over Y in somebody's preference, or the probability that X is chosen over Y in a direct comparison, is going to be represented by this formula here that has 3 parameters. So inside the brackets, I have a ratio. Okay, so X is going to be chosen over Y more frequently. First, when the difference in utility between X and Y is larger. Okay, so I'm going to be directly proportional to the difference in utility. There's going to be a utility function. I'm going to make it linear between X and Y. But before I plug it into the F, I'm going to divide. I'm going to make this inversely proportional to an inner product norm. I'm going to have a notion of distance between the objects. It's going to be really, I'm in Rn, so I'm going to make it really nice. It's going to be a norm. The norm is going to be generated by an inner product. And that's my variable of interest. That's the level of the differentiation between X and Y. And I'm going to show you in a second how it plays exactly the role that we want it to play. And that ratio, which you could interpret as some sort of strength of preference of X over Y, gets plugged into a strictly increasing continuous function that transforms that ratio into choice probabilities. Okay. So my formula, the formula that I want you to, that we're going to discuss today, has 3 parameters. It has the F, strictly increasing and continuous. It has a linear utility function, and it has a distance notion, which is going to be an inner product norm, and we will represent the level of differentiation of the options that I'm interested in. Dudi.
And for menu with more than 2?
Yes, excellent. So we're all interested in multinomial choice, and in fact, that's the main thing that referees have asked for, that people have asked of after companies. So I'm gonna prove a representation theorem using binary choice, and then I'm gonna use it in 3 applications using multinomial choice. Okay.
No, in particular, in the 2 examples that you started.
Yes. Yeah, I'll relate it to it in a sec. So the main theorem is going to say, look, my behavior can be represented by this formula if and only if it satisfies continuity, linearity, independence, and moderate transitivity. Okay, so there's going to be, the main theorem is going to say, look, this can be thought of as the data generation process if and only if the data that you see satisfies these 4 testable implications. Okay. So this is useful. Why? Because you know, when you wanted to measure differentiation or plug them into the system, you have some conditions to check directly on the data, or some assumptions like continuity that you have to make directly on the data in order to know, to have the foundations for why you'll be able to measure differentiation with the formula. Okay, this formula, first let me show you how this formula, why the differentiation here in the denominator does exactly what we wanted in the motivating examples. Okay, so think of the case of the 2 minivans. I'm going to call M1 the first minivan. I'm going to call M2 the second minivan, and I'm going to call C the coupe. So look at what happens when we decrease the price of the first minivan. So I'm making an assumption here that when I decrease the price of the first minivan, I'm increasing the level of utility of the minivan without affecting the level of differentiation between the minivans. So this is the distance, the differentiation between the minivans, and in the numerator, I have the level of utility of the minivans, and I'm going to make a usual assumption that we make in I/O, that when you change prices, you're affecting this parameter, the differentiation in the numerator, but you are not affecting how differentiated the products are horizontally. Okay. So what happens is that the derivative of the probability of choosing the minivan over the first minivan over the other, the probability that somebody ranks the first minivan as above the second minivan is going to be the derivative of f with the ratio here, and then chain rule, you have to do 1 over the level of differentiation. Now, naturally, if I make the distance between the two minivans, naturally, if I differentiate it, so I make them closer to each other, then this number here in the denominator is going to be much smaller than the number between each minivan and the coupe. Okay, so this distance or differentiation is capturing the fact that these two minivans are more substitutable than each one versus the coupe. And so when you divide by something small, you get something bigger than when you divide by something big. And then you see why the impact, or the number of people that will switch over from one minivan to the other when you make it cheaper is going to be larger than the number of people that would switch from the coupe to the minivan. Okay, so this is exactly how this formula captures the fact that some things are more substitutable than the others. That's how you need that metric to do the job. Let's go do another one. For the rectangles, or in general, when you have an agent who's in your lab trying to maximize utility and sometimes making mistakes, you have a behavioral story. Okay. You could have, let's say that the objects are in some attribute space. So I'm put here just 2 dimensions. And you could say that, like, if the agent really had all the time and all the attention and all the cognitive resources to figure out the utility exactly, that she actually has a utility function. She has these 2, I just plotted 2 indifference curves. All the objects on the top indifference curve have utility U1, okay? And that's larger than the utility of all the objects 3, 4, and 5, and 6 underneath. Now, you would expect that if you put these 2 options, 1 and 4, against each other, there's dominance there, and it's much easier to compare these 2 than to compare, for example, number 1 and number 6, right? So a logit model will not be able to capture that because you have one parameter for how good 1 is and one parameter for how good 4 and 6 are, and they have exactly the same utility. So the prediction of a logit model is that this choice problem is identical to the problem 1 and 6. And so our formula has a distance metric here that allows us to capture the fact that these 2 are closer to each other. So you put in the denominator, you put a tiny number, so you make the ratio be bigger, and so the probability of choosing 1 over 4 can be as close as, can be very big, while the probability of choosing 1 over 6 can be 60% or closer to 50%. So the level of differentiation between the options in this formula allows you to capture the fact that some problems are easier than others, even though the difference in true utility is exactly the same, because we're talking about the same gap between the 2 utility functions. Okay, so this is sort of to help you see what is the formula in motion. Where does the differentiation enter, and how exactly does it capture what we want to capture? Christoph.
No, I haven't woken up yet. So, but isn't there a kind of a tension between this example and the other example and also the drift diffusion processes, that sometimes an easy problem is when the objects are very different. Then you can decide. When they're very similar, then you can. So like what's close and what's different seems, at least at some implicit level, different in these 2 examples.
So similar and different can confuse 2 things. I can make you similar continuously. I go closer and closer and closer, and eventually become you. As we do that, I am, on the one hand, having our distance in differentiation will go to 0, but at the same time, our difference in value will also go to 0. So when we just think of the pure similarity, one object becoming the other, we're confounding the 2. This is why it's essential that we keep them separate. I'm saying, keep the gap in distance between us the same. You are going to be the better object than me. Okay, you're going to have more utility. And I'm going to go get closer to you, but I'm going to get closer to you on the same utility. So from 6, I'm going to go to 5, and then I'm going to go to 4. And once I get that close, the gap in value that existed all the time between us will become very, very obvious to see. It's just that, like, if I'm worse than you, I actually want to be more differentiated, so that, maybe I appeal to customers over here and I have a higher chance of being picked. If I'm less and less differentiated, but I'm worse, I'm going to be obviously worse, and then nobody's going to pick me.
Very nice. So I'm wondering how this is, what it adds to the one-on-one thing that we learn in I/O when you have differentiated products on a line, and they have a distance between them, and so they're differentiated, but there's also have a price. So I guess it adds something, but the idea of distance is there already in some sense.
Fabulous. So this formula is a very general formulation. Like in I/O, we all had to solve the problem that the logit doesn't do the job, right? So we came up with a million solutions. You could say like, look, I can do less than logit, I can do a covariance probit, I can do elimination by aspects, and in psychology, I can use Coombs. I have something called the Bayesian probit to explain behavior in the lab, and then some other recent papers. All of these, the idea is like, look, we came up with lots of solutions. What this paper is saying is like, all of these solutions are picking up specific functional forms for the distance and for the utility and for the f. So once we understand exactly what are all the consequences of this, we're actually doing it in a cleaner way. Just give me a metric distance, and we're going to get lessons for for a large variety of specific cases. People develop solutions, and sometimes they didn't realize they were doing a special kind of metric. Nested logit is something called a hypermetric, or like a specific metric that is a clunkier metric, but it's a metric. And so this is sort of a way of saying, let's say, a more elegant or general solution to a very general problem that's been solved in clunky ways a million times. That's my spiel. Yeah.
Let me make sure I'm getting this right. So I can understand this in two different ways. One is discernibility notion that has to do with perception. I can compare triangles better than I can compare triangles with circles. All right. Another way to think about it is horizontal differentiation a la hoteling. My preferences are location-based because I want to go to a store near my house versus a store far away from my house. And people are differentiated based on where they live, and therefore they have different preferences based on location. You're saying I can hit both birds with these functional forms.
So when we look at binary comparisons, you can hit both birds with one stone, but they're going to have very different consequences when we go to multinomial choice. So the short answer is, I'm going to show you some characterizations of multinomial choice for the heterogeneous population of rational people, okay, I/O style. And then let's say the frog paper is an example that is completely different consequences. But when you look at those in binary choices, it's basically the same. I'm going to show you how to tease that variable that is important for both settings with very different consequences, but the math is going to be exactly the same for binary choices.
Fantastic. Let me do a follow-up question though.
Yeah.
Suppose I'm sticking with hoteling. So you're capturing horizontal differentiation based on where we live. There seems to be though an implied distribution of taste based on distance.
Yes, I'm gonna pin it down to elliptical distributions.
All right, I shut up.
Yes. No, that's awesome. You're doing my job for me. Thank you. Okay, so let's go. So that's the theorem. So what I'm going to tell you is, I'm going to tell you properties of the model. Okay, so why do we have the representation model? One, you have foundations. When is it okay to say I'm measuring the differentiation? But also, you need a uniqueness result. You need to know when is it that I can pin down the f, the u, and the d, and the distance, so that I can say that I'm actually measuring the level of product differentiation. So I'm going to tell you about the uniqueness properties of this formula, and then I'm going to tell you about those 4 axioms that fully characterize it. Okay, and then I'm going to briefly mention, once we have this theorem proved for just like a general finite dimensional space, that we can bring it to have some lessons about random coefficient models of demand in I/O. I can take it to the setting of Gould-Pessendorfer 2006 and talk about random expected utility. When can you measure differentiation in random expected utility? And finally, we can go back to a problem that's been open in the abstract finite random choice literature since the 50s and the 60s, which is what happens when I just have a finite collection of objects, and we'll see what happens there as well. Okay, so we're going to have those 3 applications, but first let me go through the main formula and the theorem. So this formulation where you have an f comes all the way from the 19th century in psychology. Okay, so Fechner had this formula without anything in the denominator. Okay, Fechner only had the f and the distance in utility. It's saying, look, my ability to discriminate between 2 things depends on the gap in value. Okay. And in the 70s, Henry Haff noticed that probit and elimination by aspects and others were a particular case of taking the Fechner formula and adding a distance right here, okay, in the denominator. So the idea of using the ratio between value and distance is already in this 3-page note in the Journal of Mathematical Psychology in the 70s. what we're going to do is, instead of doing it in a finite space, okay, where, you know, he just made this observation. He said, like, look, all of these models actually take this form, and then made some conjectures about what the characterizations could be like. What we're going to do is do it in a more useful scenario where I'm going to have attributes. Assume that I have a bunch of observable attributes, so I'm in a finite dimensional space. And then I'm going to make that utility that was abstract a linear utility, and I'm going to make the distance, which was just an abstract distance metric, I'm going to take advantage of this linear space and make it a really nice inner product norm. Okay. And you see that you can write it in this way, or if we wanted to do estimation, we can rewrite this formula. So here I have a linear utility, so you can think of this as the Bernoulli index. This is a vector, okay, that has your, for your linear function. And the inner product norm can always be written as this generalized Gaussian distance, okay? So it's like Gaussian distance, but you have this variance covariance matrix in the middle, okay? So the inner product is determined by this matrix. This matrix has to be positive definite, and so you can think of the formula this way, or if you're going to estimate it, you can think of this as your variance covariance matrix, this as your vector of utility, and then you also have to estimate the exact shape of the strictly increasing transformation f. Okay, so my model will have 3 parameters. You can think of f, u, and the capital sigma. Okay, so how unique are my f, my u, and my capital sigma? So obviously, one possible transformation I can do is that I can multiply, take the old utility function that was in the numerator and just scale it up by a constant b and make a new utility function. Then I can take the old distance in the denominator and scale it up by another constant, c. So I can play around with 2 strictly positive constants, scale those up, and then undo the damage by rescaling the f. So I make the new f, the old f of c over bt. If I do that, then all of these things cancel out and I go back to the same thing. So clearly, scaling up by b here and scaling up by c here should be one of the possible transformations. But there's more. There's one more scaling thing that I can do. And I'll show you exactly what it is. So first, there's a direction in space in which the choice probability will be the biggest. Maybe it's 1, maybe it's just 0.93, but there's one direction that will be the biggest. Suppose for a second that we didn't have a generalized Euclidean distance. Sorry, let me go back. Suppose that we didn't have a generalized Euclidean distance. That means that I will use just the regular Euclidean distance, okay? So all my balls for my inner product norm will be just the standard circles. Then the direction in which the maximum probability will happen will be the direction of the utility. But because I have a generalized distance, okay, when I'm looking here at what is the direction of maximum choice probability, I'm not going to have just the utility. I'm going to have the utility multiplied by the inverse of my Gaussian, of my variance covariance matrix. Okay, so this is very easy to check. There's one unique direction of maximum choice probability, which is exactly given by this. So if you have the sigma and the u, you know what is your direction in which 2 objects are going to be maximum against each other. That direction turns out to be always orthogonal to the indifference plane in any representation. You can have multiple representations, but you look at all the objects that are indifferent to each other, there are 50-50 choices. And those, according to the inner product of this norm, they're always going to be orthogonal to that maximum choice probability direction. Okay, so I can take the space of objects, and once I have a representation, I can separate it into the dimension of maximum choice probability and the dimension orthogonal to that. Okay, so 2 dimensions. It turns out that you can scale those 2 dimensions separately. Instead of just rescaling the entire norm by a constant c, you can rescale the direction of maximum choice probability, the norm in that direction only, by a constant d, and the remaining of the norm by a constant c. Okay, so you can always talk about the distance between 2 objects as having 2 orthogonal components, and you can transform the representation and get an equivalent representation by scaling each one of those 2 components separately. So the full permitted transformations to talk about uniqueness requires 3 scaling factors, b, c, and d. So you rescale the utility by a b, you take the distance between x and y and you split it into the orthogonal components, and then you rescale one by c and the other one by d, And then it turns out we found out exactly what is the nonlinear transformation you need to do to the f to undo the damage and go back to normal. And so these are possible, and the proposition says that these are the only possible ones. So how do I get uniqueness? If I'm going to estimate, just make sure that you normalize your B, your C, and your D, and then you know that everything will be point identified. The F, the U, and the sigma are point identified once you take care of these three scaling. So it's like von Neumann Morgenstern. You can add, you can always do a linear transformation, and you have to normalize if you're going to estimate it. Here, this is exactly what you need to normalize if you're going to estimate a model in this family. Okay? So uniqueness, that tells us the sense in which I can uniquely measure the differentiation between the products. Now let's go to, this is the formal statement. Let's go to the characterization. So here are the 4 axioms. The behavior can be generated by the formula. If and only if, the theorem says that it's if and only if I satisfy these 4 things. First is continuity. Okay, so you can see from the formula that this is going to be continuous outside of the diagonal. Okay, that one's easy. Then I have linearity, and you've seen this before. This is exactly the Gould-Pessendorfer 2006 linearity. So these 2 are sort of already familiar in the literature. The ones that I want you to pay attention to and discuss more carefully are the 2 new ones. Okay, we have 2 more axioms. One is I'm going to call independence, although I'm still not sure that's the best name. So if you have a better name for me, please let me know. And the other one will be moderate transitivity. So let's go to independence. I'm going to read the statement. If x and y are 50-50 with each other, and they both beat z, so x over z is larger than 1/2, y over z is also larger than 1/2, but x actually beats z by more than y, and you give me any number between 1/2 and 1, the mixture between x and y that has a lot of x and a little bit of y has to beat z more than the mixture that has a lot of y and a little bit of x. Remember that alpha is larger than 1/2. So here I'm doing the 2 symmetric mixtures between x and y. Here I'm putting a lot of x and a little bit of y. Here I'm putting a lot of y and a little bit of x. And if x was the most powerful against z, when you mix a lot of x, you still have to get the most powerful combination against z. Okay. So I can illustrate this real quick. I think it's good to see a picture. Here's the independence. So let's say that I have a trip to Paris right here and a trip to Rome right here, okay, to do a homage to Tversky. And this is a trip to London. And London is worse than both, okay? Paris and Rome are 50-50 with each other. They have the same level of utility, but London has a lower level of utility. However, here's my generalized Euclidean distance. And if you look at the balls, you see that this circle shows how far Paris is from London in our level of differentiation. And so Paris is closer to London in this differentiation metric than Rome. Rome is in some big circle over here, okay? So Paris, because the denominator is smaller, beats London more than Rome beats London. Now, one consequence of having an inner product norm is that when I do the 2 combinations, this is the 50-50 between Paris and Rome. Here I have a lot of Paris and a little bit of Rome, and here I have the opposite, a lot of Rome and a little bit of Paris. Every time you have ellipsoids, you're going to have that this combination is going to be also closer to London than this combination, just like in this picture, okay? And so this is a consequence of assuming that the norm comes from an inner product. Let me show you how it can fail. If I don't have an inner product norm, now my balls in the norm can have other shapes. They don't have to be ellipsoids. And so here, there's another norm telling me, if I use another norm that doesn't come from an inner product, I have exactly the same situation, but notice that this square here is closer, so that this combination is closer to London than this combination. There will be a bigger square here. And so if you have weirdly shaped balls, this axiom could fail. Okay, so this is the axiom that is gonna pin down the fact that the norm is inner product. How many minutes do I have? 15? Perfect. Okay, so that's independence. I think that's not too hard to swallow. Here's the last one. Let's go to the last axiom. Moderate transitivity. And yes, there's some finesse here on what I'm going to say, but it's the following. If more than 50% of your population chooses X over Y, ranks X over Y, and more than 50% of your population ranks Y over Z, moderate transitivity requires that X over Z is strictly larger than the minimum between those two. So if this is, let's say, 60%, and this is, let's say, 80%, then X over Z has to be at least 60%, okay? So it has to be strictly larger, or you could have equality here, but the only case in which I'm going to allow you to have equality here is when they're 60%, 60%, and 60%. Okay? That's moderate transitivity. In the paper, we actually started the paper writing a lot about moderate transitivity. It's like a little discussion of the axiom at the end. That's part of the evolution. I think like we were in love with moderate transitivity, but the world apparently is not in love with moderate transitivity. But what you should know about this axiom has a long history also in the literature. When you teach a Mascolel class, there's only one way to do transitivity in deterministic ways. But when we're talking about market shares, there's at least 3 ways. So I could say that you're weakly transitive if when A beats B and B beats C, you require that A also beats C by more than 50%. Here's the moderate transitivity. It's related to the minimum between those two numbers. And there's something called strong transitivity that will be even more, require even more of the behavior. That if this is 60% and this is 80%, A over C has to be at least 80%, okay? That turns out to be too restrictive. This is the problem with logit. Logit is strongly transitive, and this is the reason that logit is too not flexible enough to accommodate the data we're interested in. When there's differentiation, you impose this, and you're in trouble, okay? So naturally, we're using for our categorization a moderate level of transitivity. You will see a lot talk about the weak and the strong in the literature. We're sort of showing that moderate transitivity can be a good compromise between having predictive power and having explanatory power. Yeah. Say it again.
Why is 1/2? I'm a bit slow because I'm tired, but why is 1/2 important here?
So, majority voting, or you have to establish how do you define a notion of transitivity? Like in Mascolel, it would be if A is always chosen over B, and B is always chosen over C, or preferred, then A has to be chosen over C.
Because row B over A is the complement? Because it's a complementary. Yes. Okay, no, that's why I was missing.
Okay, so that's the last axiom. And so the statement of the main theorem is that those are all testable implications, but those are all the testable implications. Every time you fail to reject those, you are going to be able to write the model like this formula. Okay, I have 10 minutes left. I'm going to tell you...
9. I have one question.
Yes.
So, going back to the name, so I thought that linearity is always capture the independence axiom in some sense, right? So what you show us is kind of, I just want to think again about this, what you call independence. It's some sort of monotonicity there, right? What is the role, for example, of the rho xy equal to half in the premise?
Yes, so think you're onto something. You could think, let's go back there. Real quick. Where's my row? Here. So one way to think about this is that you have some sort of independence, but only with respect to mixing with the middle point. So I'm taking Paris and Rome. Paris is beating London more than Rome. And if I mix both of them by the same amount with the middle point between them, I obtain this, and I need the inequality to be preserved. So that could be another intuition to try to find some sort of name. Okay, I'm happy to talk more about this after we're done, but let me show you what we can do with this theorem, okay? So we're going to do 3 things. And I'm just going to glance over. First, we can take this result to see what can we help the random coefficients literature in I/O. Okay, so if you look at Hausmann and Wise, BLP, NIVO, there's many estimation exercises for demand systems in which they say that utility is linear, but the vector of coefficients is a random variable. And one popular choice is to make them normally distributed. Okay? So this is clearly one particular example of our formula, because if you look at the probability that in your population, the utility is maximized by choosing X, that's exactly the CDF of the Gaussian distribution, multiplied, here you have the average beta on the top as a linear utility, and the variance-covariance matrix of the Gaussian distribution is exactly the one that gives you the inner product. So this is a specific case of the formula that we're studying today, but you're insisting that you want a Gaussian distribution for the f. Okay. So what do we learn? One, our identification results tell us something that wasn't in the literature, that you can identify these parameters just from binary data. Okay. Two, we develop an extension in which we add the price dimension. We take it to multinomial choice now. Okay, take this normal to multinomial choice, because in I/O they actually don't have just duopolies, they do multiple choices. We extend it to have a price dimension, treat price as observable, which they usually do. And we make the assumption that the price enters only the numerator. It doesn't change the level of differentiation. And then we show that you have one of these models and it satisfies our axioms, then the distribution of the betas has to be elliptical. And elliptical is just a nice generalization of the Gaussian. Okay, so this is one specific example. If you want to get all the possible f's, how much you can mess with it, go to the family of elliptical distributions, and that's exactly what you get. This result translates really nicely to the random expected utility over lotteries of Kulpe-Sandorfer. So instead of having just all of our n, we're looking just at the simplex of lotteries. But all of our results are very easy to apply corollaries, including the a characterization. So first we show, let me show something here. It's a question, right? What's the connection? Is every random expected utility model can be written in our formula? Or does any binary choice from our formula can be extended to a multinomial one that is random expected utility? The answer is no and no. They're not nested. So we show examples of how you could have one of ours that is not a random expected utility, and one of theirs that is not a binary one. But then we characterize the intersection between the two. The multinomial choices that are at the same time a random expected utility, so you can think of a population of Neumann-Morgenstern agents. It's just like the Bernoulli index is heterogeneous in the population. And that at the same time can be written in the binary comparisons with our formula, so we can talk about the differentiation between the objects. Okay. And the characterization we get is that you get the GP axioms. So we already had, in the GP axioms, we had continuity and linearity and some other things there in the paper. And then our sensitivity and our independence, and you get exactly the intersection between them. Moreover, if you allow me to charge people for the lotteries, if I add the price dimension, you not only have choices over lotteries, okay, so yes, here's 30% of winning the banana and 70% of winning the mango, but now you have a dimension in which you can charge for them. Then you get again the uniqueness. The only distributions that you can use to generate our formula come from the elliptical. So this is saying that we pin down what is exactly the shape of the heterogeneity of that Bernoulli index in the expected utility formula. Again, generalization of the Gaussian. And finally, do I have 5? Okay. 5 minutes, I want to tell you what happens when we go to a finite abstract set of options, which is a problem in which mathematical psychologists have worked for years. De Breu and others have worked on problems leading to what I'm about to do. And so what we do is, instead of having all of our n, now we just have n options and we don't know where they live anymore. Okay? It's just a finite abstract space. So we observe all the binary choices from all the pairs from some abstract set of options. So let's look at our axioms real quick. What do you think is going to survive? So where are my axioms? Axioms. Here we go. Continuity is meaningless here. So continuity goes down the drain immediately. You're not going to test continuity with a finite number of options. Linearity is also meaningless here. We're not in Rn anymore. It's a finite number of objects. We're going to throw away linearity. Independence also is going to have, doesn't have a byte. But moderate transitivity does have byte. With a finite number of objects, you could reject moderate transitivity. Okay? So in our last application, we go to this abstract finite setup, and we solve the problem that Haff proposed in the 70s. And we have the following characterization. Where is it? Where's my theorem? You have Haff's formula, just with an abstract distance, if and only if you satisfy the moderate transitivity axiom. Okay, so we get a full characterization of when is it that you can talk, even when you only have finite number of comparisons, when is it that you can represent them with some notion of distance between them. It's not going to be an inner product norm. It's just going to be an abstract distance. And the answer is if and only if you satisfy this one testable implication. This is really nice because you can go to data, and this is very easy to test. I had a bunch of examples to show you. But instead of that, I'm going to tell you how this third application to a finite abstract space completes some sort of research program that is very long. So you now have a complete staircase of formulas where our formula is here, okay? This is the half formula with the utility and the distance and the F, okay? That's called that a moderate utility model. And in one of our applications, we show that this is equivalent to being moderately transitive. And now we have the complete staircase in order of generality. You can impose something stronger, which is strong transitivity plus, and it was known by Tversky and Russo. There was a characterization of a model they called simple scalability, where you don't have a distance and you just have an F that depends on the utility of X and the utility of Y. If you go even stronger and you impose something called acyclicity, you have a result by Fudenberg and co-authors of that characterizes Fechnerian utility. Okay, so it's exactly the same formula but without the distance. And if you go even more specific and you impose something called the product rule, you get exactly the logit formula. Okay. So we can go all the way down from our formula all the way to logit. But we also got, as a bonus, a last proposition where we say, hey, what if this distance doesn't really need to be a metric? You do just a semi-metric, and we relax the triangle inequality. Well, then it's going to be very easy to plug any denominator you need here. The only consequence that is going to be left is that you're still going to be weakly transitive. So weak transitivity is equivalent to this that we call a weak utility model, where you throw away the distance. What does that tell us? The gap in behavior between moderate transitive and weakly transitive is equivalent on this side to the triangle inequality property of our differentiation metric. Okay? And so that's our third application, and I'm going to stop here and take any questions. Thank you very much. I'm going to show you some data then. There's no questions, I'll show you data. So you take this to data, you take any data set, and the moderate transitivity is super easy to test. Oh my God, I have so many slides. I was going to do it on the iPad, and so I had to produce the PDF, and I think a lot of stuff made it. Let's find my data sets. You see the proof? Okay. You see that picture? So just a curiosity. If you're interested in random choice, if you're a guy interested in random choice, of course you're Oops, 1965. So this problem, that staircase that I just showed, it's something that we've been working on for a long time. So yeah, a long time ago, already the moderate transitivity, strong transitivity, and weak transitivity postulates have been proposed. They just hadn't been characterized yet. So that figure with the staircase that I showed you is the modern version where this program here is completed. So that's a neat observation for you to compare. Anything else? Where am I? Here's the data. So that data, remember that the two triangles were easier to compare? So this one is chosen over that one 85% of the time, and this one is chosen over that one 50% of the time. To be strongly transitive, like logit, you would need the first one versus the third one to be at least 85, larger than the maximum. Too restrictive. But this one is still larger than the minimum, so it satisfies moderate transitivity. Okay. And directly testable. You just eyeball it. You don't have to run a regression. You can just use the moderate transitivity as a sort of non-parametric test for what's going on. Here's another one. Here's my favorite data set in the world, the frogs, that I use in another paper. B is chosen over A 63% of the time. A is chosen over C 84% of the time. If you want it to be strongly transitive, you will need B over C to be at least 84. But it's not. It fails strong transitivity, but it's still moderately transitive. And then this is asking, this is screaming, please fit a model with an F, a U, and a sigma, and tell me what is the differentiation between A, B, and C, and what was the utility. That's what I did with a specific parametric form in a previous paper. All right. That's it. Thank you.
Thank you.